Hi everyone, welcome to Rotational Motion. We're going to be talking about static equilibrium this time. This has a lot to do with torque, but now it's also a little bit different. Static equilibrium means when the net forces of an object is equal to zero and also the net torque of an object is equal to zero. This is the most important thing to know when it comes to static equilibrium. The reason for this is because nothing is accelerating up and down or left and right like this plank, and nothing is rotating clockwise or counterclockwise. So if nothing is moving or nothing is rotating, that means it's in static equilibrium. So let's read this problem. A child of mass 43 kilograms, so this mass 43 kilograms, is supported on a plank that is 10 meters long, with negligible mass, who exert the forces F1 and F2. So we can see that there's an F1 we don't know and an F2 we don't know. Okay, and we're trying to find what those forces are. Key thing to know when something is not rotating like this is you can make the point of rotation wherever you like. And where you usually want, since you can put it wherever you want because nothing is rotating, you want to put it at the place where you don't know where one of the forces are. So we don't know what F1 or F2 is. I'm going to put the point of rotation at F1 just because I think that's a bit simpler, but you could have also put it on F2 if you would like. Now, once you make that point clear, now you want to find the torque with all the different forces. So let's find the torque of the first one. We don't know what F1 is, but the radius is going to be 0 because it's right where the point of rotation that we made was. So that's 0. Torque 2, that's going to be with this person here. So this is going to be 430 newtons. So it's going to be F2, which is 430 newtons, times the radius. Oh, this is good to know. So this is going to be 7.5 meters times sine. And since it's just the weight, that's going to be a 90-degree angle right there. Okay? So sine of 90. Let's put that in our calculator. 430 times 7.5. 3,225 Newton per meter. So it's important now, okay, if we were to just look at this force, which way would it rotate? So this is the point of rotation, and we see if we just looked at this force, it would rotate this way, which is clockwise. So if it's rotating clockwise, we want to put this as negative. Now let's look at the other force. Torque 3 is equal to F2, we don't know what this force is, times the radius, it's 10 meters away, times sine of 90. So we don't know what this is. However, what we should know is the net torque is equal to 0. So if the net torque is equal to 0, we know this is negative 3,225 and this is 0. That means this has to be positive 3,225 Newton per meter. And now that we know that, we can find what force 2 is equal to. So now I'm going to do force 2, 3,225 divided by 10. Sine 90 is just 1, so we don't have to worry about that. So this is going to be 322.5 newtons. Okay, that's how much this guy's pulling with. Now, for this lady, we don't know what this force is still, but remember, we know that the net force is equal to 0. So F1 plus F baby plus F2 should all equal 0. So F1 we don't know. The force of the baby is negative 430 because it's going down. Plus F2 is 322.5. So we now know that F1 is going to be equal to minus 430, 107.5 newtons. Okay? And it should make sense. Since she's further away from where most of the weight is, that means it's going to be easier for her to lift than this person here. All right, moving on. The figure shows a force being applied to one end of a lever, length L. What is the magnitude of the torque of this force? So we can see there's in length L. There's a force. I'm going to put this force like this. Oh, sorry, that is not straight. I'm going to put the force, even though it's pointed down like that, I want to point it like this down. Okay, and this force was P. So again, we should know that torque is equal to force times radius times sine of theta. So we know the force is represented by P. We know that radius is represented by L. So, force P times L. Now the tricky part is theta. We know this theta here, but we want to know what this theta is right there. What we should know is that this angle right here is equal to this angle here. I'm going to call this theta prime. Okay? So, and what we should also know is this theta here, cosine theta, is equal to sine theta prime, if we remember that from our math class. So what we can say is, we don't know what this theta is, but we can say that this sine here, sine theta prime, is equal to cosine theta. And then this is our answer right here. P times L times cosine of theta. That might have been a little bit tricky, especially if you don't remember that math as well in your geometry class. But that's how we do that problem. Alright, now let's look at this one. A cat walks along a uniform plank that is 4 meters long. Okay. 4 meters long. Okay. And has a mass of 7 kilograms. So this plank has a mass of 7 kilograms. So that's important to know. So we know that the force is going to be acting directly in the middle if something is a uniform, right in the center, I should say, the center of mass if it's a uniform mass. So this is going to be 70 newtons, the weight of it. The plank is supported by 2 sawhorses. So 1 sawhorse, 2 sawhorses. One is 0.44 meters from the left of the board. Okay, so this is going to be 0.44 meters, like that. And the other is 1.5 meters from the right of the board. Okay, so 1.5 meters from the right of the board. When the cat reaches the right end of the plank, it just begins to tip. What is the mass of the cat? So we're looking for the mass of this cat. Okay, a bit tricky. So this shows that there's no force here. I guess because it's just about the tip, so there's no force here. However, there's a force here we don't know, and we don't know the mass of the cat. So again, you want to put the axis of rotation where we don't know where one of the forces are. So we could put it by the cat if we wanted to, but I'm just going to put it over here since we're looking for what the cat's mass is. You could have done the cat, it would have been fine. So let's look at all the different forces. There's no force here, so I'm not going to label that, but I'm going to put this one as 1, I'll put this as 2, then I'll put this as 3. Alright, so let's find the torque of each of these. So number 1, torque 1 is equal to the force 70. Next we don't know what this is, but we do know that it's right in the middle, so this is going to be 2 meters. So from here to this axis of rotation that we set, it's going to be 0.5 meters. Okay, if this is 1.5, that means it has to be 0.5. So it's going to be 70 newtons times 0.5 times sine of 90. And let's put this in our calculator. Oh, that's going to be 35 newtons. I don't need to put that in my calculator. Newton per meter. And now let's see. If this is the axis of rotation and we were to just look at this force, it would rotate like this, counterclockwise. So we're going to call this positive. Next, T2. If we look at T2, we don't know what F2 is, but we know the radius is 0. So we know that this is just going to equal 0. Because it's right at the axis of rotation. Torque 3 is equal to, we don't know what the force of gravity is of the cat. But we do know that the cat is 1.5 meters away from the axis of rotation, and it's acting perpendicular, so let's figure out what this is. Next, what we don't know is, we don't know what this torque is. But remember, when we're doing problems with this, the net torque needs to equal 0, along with the net force. So, if torque 1 was positive 35 Newton per Newton meter, and number 2 was 0, that means this has to be negative 35 Newton meter. Now we could do some physics. 35 divided by 1.5, or some algebra I should say, and we get 23.33 kilograms. Oh, not kilograms, newtons. Okay? And then we should know that this is equal to mass times gravity, so we're going to just divide this by 10, and then we get 2.33 kilograms. Okay? Oh, should be 2.33. I forgot about that last time. Divided by 10. Alright, sounds good. Alright, so let's move on. Alright, so this one looks pretty complicated. We're just looking for what is mastery. You know, I guess it's some pretty heavy brick. You might have seen like these kind of mobile problems before, but this becomes a bit difficult. Okay, so you want to look at, okay, which one do you want to solve for first? And we have M1 we don't know, M2 we don't know, and then 0.3. So first thing we want to do is we want to set up some equations. We know the torque of this side is equal to the torque of this side, and that's why it's not moving. And we know the torque of this is equal to the torque of this. The torque of this is equal to the torque of this. So a lot of these torques are equaling each other out. So let's just try to simplify certain things. Okay, let me look at this 1 and 2. So torque 1 is equal to M1. Let me just write it out actually, because this might confuse people. So torque 1 is equal to force of 1 times radius times sine of theta. So for this one, I'm just going to call it M1 times G, because that's the weight of it. That's how much it's pulling, the force. And the radius, I'm going to say 0.12 meters. But I'm not going to even use sine, because for all of these problems, it's all equal to 90, which is just equal to 1. Okay, so I'm not going to use that. But what I should know is torque of 1 is equal to torque of 2. So these two are equal to each other. We should know that, because if they weren't equal to each other, they wouldn't be stable. So I could say M1G times 0.12 is equal to M2G times 0.18. That's the radius. Okay, torque of 1 is equal to torque of 2. What I could also do is I could get rid of gravity. Whoops. I could get rid of gravity because gravity cancels out on both sides. Times 0.2. So I'm going to get gravity. Okay. So now I'm left with this equation. M1 0.12 is equal to M2 0.18. So that's going to confuse things a little bit. So now what we're going to do, we just looked at this axis. Now let's look at this axis over here. So let me put this over here. What I know is this stake here, let's call this 3. The torque of 3 is going to be equal to both of these combined, everything going down this way. So I'm going to say mass 0.3 times gravity 10 times the radius 0.24. Okay, I'm not going to do sine because that's just 1. So I know that this is going to be 0.3 times 10 times 0.24 is equal to the torque of everything going down this way. Okay, so let's try to figure that out. So the math, we don't know what this is, M1 plus M2. Gravity, which is 10. And then, but we do know that this is 6 centimeters away, so we're going to call that 0.06. 10's cancel out, so let's just leave that alone. And now we have, and let's try to simplify this. 0.3 times 0.24. 0.072 is equal to M1 0.06 plus M2 0.06. So now what we have is we have 2 equations and 2 unknowns. We don't know M1 and we don't know M2. So let's try to simplify this a little bit. I'm going to say M1 is equal to M2 times 0.18 divided by 0.12. So M1 is equal to M2. And let me just put this in my calculator. 0.18 divided by 0.12 and get 1.5. Okay, so now I know that. Now I'm going to plug that in right here. So 0.072 is equal to M1, is going to equal to M2 1.5 times 0.06 plus M2 0.06. Oh God, everyone's lost. It's all right though. 0.072 is equal to, yep, that's 0.06. M2 times 0.09 plus M2 times 0.06. So we can simplify this. 0.072 is equal to M2 times 0.15. So now we can say M2 is equal to 0.072 divided by 0.15. Oops. 0.072 divided by 0.15. And we get M2 is equal to 0.48 kilograms. This 0.48 kilograms. Now, if we wanted to find what M1 was, we could just put into this equation. So 0.48 times 1.5. And then we see that this is equal to 0.72 kilograms. Okay. Now, last, we have to find this bread. Let's get this bread here. Get this bread. Yes. All right. So now let's look at this axis here. So this is going to be a little confusing. Okay. Let's figure this out. So this side here is the torque of this is going to equal the torque of all of this. So let me just get this side out of the way. M3 times 10 times the radius, 0.31, we don't need to include sign because it's just 1, is equal to all of these masses combined. So 0.2 plus 0.3 plus 0.48 plus 0.72 times 10. So all this mass is pulling down on this string here, which is 0.18 meters away. 0.18. 10 cancels out. So let's do M3, and then let's put that 0.31 on the other side. But let me simplify this a little bit. 0.2 plus 0.3 plus 0.48 plus 0.72 times 0.18 is equal to 0.306. And then now let's divide this by 0.31. And we get this bread is equal to 0.99 kilograms. Heavy bread. A lot of bread. All right. Hopefully that wasn't the worst thing in the world, but maybe it was. All right. Now we're going to start looking at a few harder problems. Again, remember, when nothing is moving, net force is equal to 0, and net torque is equal to 0. Okay? Key thing to know. Okay. So a traffic light hangs from a pole, as shown in the figure. The uniform aluminum pole is 7.2 meters from A to B. So this is 7.2 meters. Okay. And has a mass of 11 kilograms. So it's a uniform. So we know right in the middle of it, we can put the force of gravity, which is equal to 110 newtons, which is also going to be 3.6 meters from this pivot point if we want to use that. The mass, okay, and has a mass of 11 kilograms. The mass of the traffic light is 20.5 kilograms. So, okay, so we also know this gets pulled with a force of 205 newtons. Determine the tension in the horizontal mass scale. Okay, so this is where it becomes a little confused. So we want to find what this force of tension is. Okay, we know there's a force weighing down here, force weighing down here, and there's also going to be a force over here keeping this pole up. I'm going to call this force of pull. Okay. Now that we know all those forces, let's label them. Okay, 1, 2, 3, and then 4. Okay, these are all the forces on the pole. So part A. Number 1. The torque of 1 is just going to be 0 because, again, the radius is 0. Okay, if we're making the radius of rotation right there 0, then that's just going to be 0. Number 2. So if we're doing this, the torque 2, force is going to be 110 times the radius, 3.6, times sine. We can't do 90 anymore because it's not 90 degrees. We need to figure out what this angle is right there. Okay, we need to figure out what that angle is. Okay, and what we should know is this angle here, and if we were to make another angle right here going straight down, this angle here would have to equal 90. So this would be 90 minus 37, so this is going to be 53 degrees. Okay, so what that means is this angle here is 53 degrees. And this angle here, also for this traffic light, is also 53 degrees. Okay? Because from here to here, 53. All right, sine of 53. All right, so let's put this into my calculator. 110 times 3.6 times sine of 53. 316.26 Newton per meter. And if we were to just look at this, we would see that this would go clockwise. So that means this we were going to put this as negative. Now the third one. Torque 3, the force 205. It is 7.2 meters away times sine, and again it's going to be 53, okay? Because remember, it's between the force and wherever the rotation is. So that's going to be where it wants to rotate. So then we have 205 times 7.2 times sine of 53. And now we get negative, because again it's going clockwise, negative 1,178.8 Newton per meter. Now number 4, torque 4, it says, okay, we don't know what the force of tension is. Okay, we don't know what the force of tension is. Oh, wow. We actually don't even know the length of this. So this is a little bit confusing. Man, there's so many. I know everyone's probably confused here. Okay, so if we did this, we can find what this length is, though, but we're going to have to use sine. So we should know sine of 37 is equal to opposite, which is 3.8, over the hypotenuse, which is going to give us how far it is from the axis of rotation. So let me just figure that out real quick. So 3.8 divided by sine of 37, and we get 6.31. Okay, 6.31 meters, and it's going to be times sine, and the angle is going to be, this is where it's rotating, and this is the force here, so this is going to be 37 degrees. Sine of 37 degrees. So I don't know what it is because I don't know what the force is. However, since I know the other torques, I can figure out what this torque is. It should be the opposite of both of these. So 1,178.8 plus 316.26. And this is going to give us 1,495.06 Newton per meter. And this is going to be positive. Now that I know that, I can find what the force of tension is. I'm going to divide this by 6.31. And then I'm going to divide it by sine of 37. And then I get 393.7 Newtons. Okay. I know that was probably pretty difficult. Alright, so now let's look at part B. Determine the force exerted by the pivot on the aluminum pole. Okay, so this is where the net force comes along. Okay, so we know that this is holding everything up. So this is dragging it down. So we know that the force in the y direction, force of the pole in the y direction, has to cancel out with everything getting pulled down. So that means that this is going to equal, let's see, 205 going down, 110 going down. So it's going to equal 315 newtons going up. So it's trying to keep it up with 315 newtons of force. And now the force of the pole in the x direction. So we know for this pole is getting pulled to the left with the force of 393.7 newtons. So that means it has to go to the right. Whoops, I should make this force of the pole. So it should be going to the right 393.7 newtons. Okay? And then once I have that, I can make a little triangle. 393.7, and then 315, and then this will give me the force of the pole. And then that'll equal to 504.2 newtons at 38.66 degrees. Hard one. Okay. One more hard one. Let's see if you guys can figure this out. Ooh, this is tough. All right, last one. Here we go. An 85 kilogram person stands on a lightweight ladder that has a mass of 8 kilograms with a length of 4 meters, as shown. The floor is rough, hence it exerts both a normal force and a frictional force, okay, F2, on the ladder. The wall, on the other hand, is frictionless. It exerts only a normal force, F3. Using the dimensions given in the figure, find F1, F2, and F3. Okay, this seems kind of crazy. So we have F1, normal force F2, and then F3 going this way. They don't show the force of gravity of the ladder. So force of gravity of the ladder, and then force of gravity of the person. Okay, force of gravity of the ladder. The ladder is 8 kilograms, so this is going to be 80 newtons. Force of gravity for the person, 85 kilograms, so this is going to be 850 newtons. All right, let's figure this out. So, looking at this problem, okay, let's see, 4. Okay, so we know this whole thing is 4 meters long. 4 meters long, so that means this is going to be 2 meters halfway through the ladder. We know that this person is up 3.8 meters, but we don't know where he is exactly. Okay, so next thing that we need to find out is we need to find out this angle. So if we know this is 4 and this is 3.8, we could figure out what this angle is right here, or the bottom. So what I'm going to do to find out that angle is I'm going to do inverse of cosine. Cosine inverse, and this is going to be adjacent, which is 3.8, over hypotenuse, which is 4. It's going to give us theta. Let me put that in my calculator. 3.8 divided by 4. And I get 18.19 degrees. So I know this angle right here is 18.19 degrees. That means this angle here is also 18.19 degrees. And this angle here is 18.19 degrees. Okay? So that's important to know. Okay, now let's kind of label things. So I'm going to label this 1. I'm going to label this 2. I'm going to label this 3. Label this 4. And label this 5. So torque of 1 is going to equal 0, because I'm going to put the axis of rotation right here, because I don't know what F1 is and I don't know what F2 is. Torque of 2 is also 0, because right on, again, the axis of rotation. Torque 3, now I know what this is. That's from the ladder. The force is 880. The radius, I guess, oh, that's going to be 2 meters up, because it's going to be halfway, because it's a uniform mass ladder, times sine, and I found out that this is 18.19. So let me just put that in my calculator. 80 times 2 times sine of 18.19. That gives me 49.94 Newton per meter. And now let's look at this. If we look at this, this is the axis of rotation. This goes this way. That's clockwise. So we're going to put that as negative. Torque of the third one, this is from the person. This is going to be 850 newtons. We don't know actually how far he is from the axis of rotation. We don't know what that is, but we do know that he's 0.7 meters, and we do also know that this angle here is 18.17. So let's use sine to figure this out. So sine of 18.19 is equal to opposite 0.7 divided by hypotenuse, which we're looking for. Now let's put this in my calculator. 0.7 divided by sine of 18.19, and I get 2.24 2.24 meters. So that's going to be 2.24. It's going to be times sine. Again, it's the same angle. It's the same small angle here, which we found to be 18.19. Let's put that on a calculator. 850 times 2.24 times sine of 18.19, and we get 594.4. And again, if we were to see this one rotate from this, the force, that would go clockwise, which would make this negative. Now, torque of the fifth one. So we don't know what the force is, F3. We don't know what that is. We do know it's going to be all the way at the end, so that's 4 meters long. We don't know the angle, so we know that this is 18.19, but we don't know what this angle is over here. However, we should know that this is a 90-degree angle, so if that's 18.19, we're just going to minus that by 90, and we get 71.81. Now let's, and we don't know what the torque equals to, because again, we don't know what F3 is. However, we should know, since the net torque should equal 0, that means it needs to cancel out with this. So let's put that. 49.94 plus 594.4 is equal to positive 644.34 Newton meter. Okay. Now that we knew that, let's divide by sine of 71.81 and then divide by 4, and we get F3 is equal to 169.56 newtons. Okay. Okay, now we have to find F1 and F2. Again, we have to know that F net is equal to 0 because it's not accelerating up and down or left or right. What we should know is if F3 is 169.56, F2 also have to equal 169.56, but in the opposite direction, so they cancel out. Okay? And then for F1, F1 needs to cancel out with the force of gravity of the ladder and the force of gravity of the person. So 80 plus 850, so this is going to give me 930 newtons. Okay? And that's what we should get. That's what we get. Whew! That was a bit rough, but you guys got it. Thanks for watching, everyone.